Good day, dear students. Welcome to the part 2 of the lectures on covalent bonding. So we'll just start. Okay, so you guys will notice that it's almost like I'm confused with where the location of the slide is and where I am. I just decided to stick with Google Meet formats because it worked. So we're going to continue with resonant forms. If you hear the word resonance, what comes to mind is resonating. As I'm speaking to you, my vocal cords are resonating, my voice is resonating as well. Hence, if you're in a room without the open space, your voice will resonate and echo and all of those things. So we have forms, and this is an extension of something moving. It's movement. The word resonance, movement. So in certain cases, low structures do not represent chemical or physical reality. I've said this before with the students. I said a picture or even an image is not you. It's just a reflection of you. If you look at the mirror, what do you see? Question that requires an answer. If you look at the mirror, what do you see, or who do you see? People go quickly and say, I see myself in the mirror. Really? So if I was to push the mirror, did I push you? No. It's just an image of yourself or a reflection of yourself. Hence, the right thing or the more accurate thing is an image of yourself or a picture of yourself. Because people draw pictures and squeeze them and put them in the bin. Did they squeeze you and put you in the bin? No. So here's the concept of resonant forms. They're just forms and they're on paper. They just are trying to represent what exactly we're seeing or we know of. So we have an example of SO2, and we saw that previously. Let me take it back so that we saw that here when we're trying to describe and explain how we draw low structure. Notice that we have an idea of what it looks like, but we just want to explain our way to what we know about it so that we can do for others we have no clue about. So let me go back to where we are. We are looking at resonance structure. So your SO2, remember we said there's a double bond that is moving. Hence, you can have two forms which are called the resonant forms. One on this side and the other on the other side. So notice this is the symbol for resonance. An arrow pointing both ends, meaning that it can either be this or the mirror image on the other side, which is the resonance. Just simply means that this double bond is moving from here to here and here to here. I hope that makes sense. If it doesn't, let's keep going. Remember what I said previously. Notice that you have 1, 2, 3, 4, 5, 6, 7, 8 around sulfur. Then you have 1, 2, 3, 4, 5, 6, 7, 8 around oxygen. Then this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So octet rule. Just put that at the back of your mind. But notice that we're going to see some exceptions ahead, and we'll explain why those are exceptions. So we have another example, and this resonance structure is not SO2, which is a compound, but it's an ion. So you can have resonance structures in ions as well. So given that we're in North Cyprus, most of us, I used to say, okay, this is Lefkosia. No, this is Magusa, this is Lefkosia, and this is Guinea. The reason why I did that is that Lefkosia is kind of central, and then the other places are the end. So Magusa, Lefkosia, and Guinea. So notice that it's just movement. The double bond was in Magusa, then it moved to Lefkosia, then from left kosher it moved to kidney. So notice that the double bond is mobile, meaning that it's all in the same location, but we're just tracking the double bond. And in all of this, what is moving is not the oxygen, it's not the nitrogen, it is just the electrons. So very important that you put at the back of your mind. So that's it. And you cannot have a double bond and then 6 oxygen on top of that. Notice that they are all obeying the octet rule. So you have 2, which is 4 here, another 2, which is 6, another 2 here, which is 8. So notice the balance. So let's go. So we have benzene. Benzene is an aromatic hydrocarbon and it has double bonds. And the double bonds too move, just to explain in deeper details what the resonance are. So notice that the double bond can be here or here. The next one can be here or here. The other one can be here or here. Notice that if you have one double bond here, there's not going to be another on the next. Then you have another. So it skips one and goes to the next. So you can also use a cycle, which means that it goes round and round. Hence the cycle to indicates resonance. So I think we're clear on that. So resonant forms are not different molecules. Very clearly, I said it's still Lefkosia, it's still not Cyprus. You're just in different locations in the same place, and what is moving is you, not the place. So nor are they representative of electron shifting. So they are not, because their electrons are shifting doesn't mean that they are. It's just how we are trying to explain resonance. So resonant structures arise from two Lewis structures. Arise when two Lewis structures are equally pulsable. So only electrons can shift in resonant structures. As I said earlier, it's only electrons, not compounds. Atoms cannot be moved. Cannot be moved. You don't move atoms. So, and if you feel like moving an atom, tell yourself, no, we don't move atoms, we only move electrons. So that's what the resonance. By the way, I said it's a representative of something. So it's your own representation when you move atoms, and yours might not tally with the general body of chemistry. But know that what we have agreed on is this: electrons are what moves with resonance structure, not the atom. So we have an example here, and I would like you to, given that you know what SO2 looks like, attempt to draw NO2 minus, which is an ion, and an ion for that matter. So can you please pause the video and attempt to do this? Just draw a resonance structure. How many resonance structure and can it form? Know that you have to have two for starters, and when you have O2, can I get the idea that basically it's 2 that might come out of O3? We saw 3, right? NO3 minus, we saw 3. So give it a try. I'm waiting for you. Okay, now that you have either attempted or just kept on watching, let's just go into it. So this is what it's going to look like. You're going to have your 6 on one side, and then the double bond on the other with just 2, and then a lone pair on top of the end. So at the end of the day, you have 1, 2, 3, 4, 5, 6, 7, 8 nitrogen, 6 on oxygen, and 6 on the other oxygen. So the change in position of the electron pairs will just be this way and this way for you to have the other resonance structure. So it just doesn't change the skeleton. So this is what it's going to look like. And always remember, when you're drawing your Lewis structure, if you have an ion, put it in bracket and indicate the charge. Never forget to do that. So we have what we call formal charges. It's very important that you understand formal charges. So the word formal, you either are formal to someone or informal. Formal will mean you being respectful or being more polite or modest. And informal will be what you do with your friend. You just can call a friend anyhow, you can just be free around them. But with formal, you have to have a. So in this case, talking about charges and formal charges, and we're talking about the actual charge on something, because electrons have that and it's charges, so it's ion related. So the difference between valence electrons in the free atom and number assigned to them within a Lewis structure. So notice that there's valence electrons, and then there's the free electrons, and then you have numbers assigned, charges. Notice that we're talking about charges. So analogous of oxidation numbers is actually related to oxidation number. So I'll explain that as well. The word oxidation, oxidation, oxygen, oxidation, it's a process. Oxidation number, notice the value attached to that. So they are not actual charges. Again, establishing facts. They just keep track of electron ownership. So remember, we talked about electron ownership in the last class, or part 1, not last class, part 1. So, and this is just trying to help us know who has what. So actually there's a formula for it, and it's actually formal charge is equal to the valency electron minus number of unshared electron minus number of bonds. Notice that if you look at it very closely, you have valency electron, number of shared electron, which is individual electron, and then number of bonds, which is bonds. So you're trying to track something, what charge is left hanging. So let's see more rules that govern formal charges. So the quality of Lewis structure can be determined by the distribution of formal charge. So if you want your Lewis structure to be very accurate, then distribute the formal charges evenly, or check for the presence, or know where there is or there's none. So minimize charges. So it's best to have no cumulative or small cumulative. Sorry, CF is actually formal charge. It's formal charge. The CF is formal charge. So either you have no formal charge or small formal charge. Thinking about cumulative. So when you remember, we did in the last lecture, some lectures before, we did electronegativity, and we said this is the intrinsic ability of an electron to draw, of an atom to draw electrons to itself. And we said the most electronegative, or tongue twister, the most electronegative is fluorine, and then the least is cesium. And fluorine has 4.0 like a GPa, and cesium has 0.8. So the most electronegative atoms should have the most negative formal charge. So I think we've done a lot of talking. Let's look at an exercise. So when you're calculating formal charge, there are things to consider. You're going to be considering the individual atoms. Take for example CH3OH. You're going to be looking at carbon, hydrogen, the different hydrogen, and then oxygen. So the formal charge for carbon is 4, and 4, remember, is the valency electron. Then minus the the unshared electron, which is 0 because carbon doesn't have any unshared electron. Then the bonds is 4 because carbon is tetravalent, so your bond is 4 plus. So if you do that, 0 is going to be your answer because it's like 4 minus 4, which is 0. Then you do for oxygen. And oxygen, you have to do, the valence is 6 minus the unshared, which is 4 unshared electrons. And then most times you have carbon bond in 2 places, or it should bond in 2 places. Then you see 2 bonds. So at the end of the day, minus that through 0 as well, which is 6 minus 4 is 2 minus 2, 0. So notice that for hydrogen, no heat, it's going to be the same situation. So you have a formal charge of 0 all through on that. So hence we said previously, minimize charges, best have no formal charge or small formal charge. So we have exceptions to the octet rule. Told you previously that there were some exceptions. There's always an exception. You always will have some people that will just love to break or disobey the law. So there's what we call electron deficient molecules. So these molecules, they kind of like lack. I told you guys when we were talking about vitamin C, we talked about the deficiency of vitamin C, and some people gave me some very weird answer, and we discovered that it's called scurvy. Scurvy is deficiency of vitamin C, and then you have a sign that you have scurvy is bleeding gum, mostly bleeding gum and all of those things, and your immune system will be down, very down. So electron deficient molecules are the ones that tend to stand and pose as exception to the octet rule. So all the electron species which are free radicals, they are what we call free radicals. Free radicals are just elements that have a sense of charges and all of those things moving around, so they could call them free radical. And then you have the paramagnetic, and the paramagnetic ones are the ones, notice that the previous ones are called odd electron species. You know, it's odd, even. Odd is like one shot, even is even. It's like 2, 4, all of those things are even. Odd numbers are the ones that are just alone. That's why they call them odd. Then you have paramagnetic, and paramagnetic molecules, if you remember, we said those are the ones that they don't have they're not paired on the orbital. They just have one. Everything is just parallel, pointing up. But when they are diamagnetic, they are together, one pointing up, one pointing down. I hope somebody understands that. So those are and they are called electron deficient because they are lacking, or they're just alone. They are almost like an island in an island alone. So examples are your NO, NO2. Very interesting. They are the ones that get you confused, because if you look at NO now, what's going on there? This is 1, 2, 3, 4, 5, 6, 7, 8. Okay, good for oxygen. But nitrogen is 1, 2, 3, 4, 5, 6, 7. What's happening? Hence, you have a confusion on your head if you're thinking about it. How? Is there something that we don't? But there's a compound called NO. But the question is, we are trying to represent it using Lewis structure, but we can't, because it's almost like, so these are the exception, because it can be explained using Lewis structure or the octet rule. Hence you have a situation in your hand. So you have this one as well, which makes you wonder if it's an ion or it's a compound. Actually, it is a compound. There's NO2. So now If you count it through, 1, 2, 3, 4, 5, 6, 7. So you have this situation and it forms a resonance as well, which makes it interesting. So there are possible structures for beryllium fluoride and boron fluoride. So notice in this case, notice the difference in formal charges. In this case, -2 plus 1. In this case, 0 and 0. So you see that the formal charge varies based on the structure. Very important. Hence, the whole idea of the difference that you can get on the strength of understanding what the formal charge is and how it helps you draw the low structure more effectively. So, same thing, just different formal charges and also different structure. So you have structure 1, structure 2, formal charge 1, formal charge 2 of the same thing. So hence you know that there is a problem when you are dealing with this. So there are exceptions to the octet, and then they pose an issue with the formal charge thing, because the octet rule is what helps us stay on point with the formal charges and with the low structure. So exceptions to the octet rule are your molecular oxygen, which is your O2, the one we breathe in, and then the paramagnetic atoms. Although it has even number of electrons, it exists as a diradical. So the word diradical, if you know what radical is in English, is somebody that is very unstable. So when you say diradical, it can only stay with 2 of itself, because you need people that move around a lot always need people that move around a lot as friends, so that it can help the motivation keep on going. So you have that. So it's a pair of electrons. So the pair is 2 unpaired electrons. So you have 2 unpaired coming together to move around. That's why you always see oxygen O2. And you can have examples like hydrogen, H2, all of those different. And remember, we're talking about energies. The energy has to be low enough for them to lock in and bond together. So low structure is difficult to draw for this kind of exceptions. So let's go into it, and then we have what we call the expanded octet. This one is the octet rule expanded. So some elements are capable of surrounding themselves with more than 4 pairs of electrons. So these ones are like they carry extra, and notice that because of the extra, it's going to affect structure, it's going to affect even the drawing or representation of it. So expanded octet, you have examples of phosphorus pentachloride, sulfur hexafluoride. So because these guys are in group 15, 16, 17, and you have some noble gases too as well, krypton and xenon. We'll see examples. So this phosphorus, arsenic, antimony, sulfur, thallium, and selenium. So you have all of this, your chlorine, bromine, and iodine. So these are the expanded octet. So for these ones now, it gets interesting. So I'd like you to pay attention to something. So you have the chlorine and then 3 fluorines. You have chlorine and 3 fluorines, and notice that it's already looking strange, because you were wondering what's going on. We said it's covalent bond, and most of the covalent bonds happen with people in the same group, which are mostly non-metals. So don't get yourself confused, like, teacher, they are in the same family, why will they be bonding together? Yeah, you have that kind of a situation in chemistry. So you have this, and the skeleton naturally the bonds will happen in 3 different places, because you have 3 fluorine and then 1 chlorine. So if you look at the electrons around about them. For chlorine 7, fluorine 7 times 3, which totals to 28. And then if you look at the bonds, 3 bonds, so the 3 times 2 is 6 minus 28, which is the total electron around them, that's valence electron. You have 22. So from that 22, you now work out the mass like we did the last time. You now say, okay, for the 3 fluorine 6s, the 6 around about them, so 6, and then for chlorine is 2. What you're trying to do is to find out the needed, and then you compare it to the available. Needed equated to available, and you're trying to find out if it's short. If it's short, you're now fixing a double bond, because notice that this is 22 and this is 20, and when you equate 22 and 20, you know it's 2 electrons short, because what we're doing is electrons. We're taking electron. We say available electron is equal to needed electrons. If it's not, you have, well, how short is this? Is it by 2 electrons? If it's by 2 electrons, you just add a double bond. And when you add a double bond, add an extra. So in this case, what we do in this case is that we put a pair of electron, not a double bond now, because if you add a double bond, you have a whole lot of issues. So you put an extra on chlorine, that makes it the expanded octet, where it doesn't have 8 now, it's going to have 10 for balance sake. So that's first. And then we have an example of xenon and fluorine. Remember, I told you that electronegativity is the intrinsic ability of an atom to pull electrons to himself, and we said fluorine is the most electronegative. So hence, you see the whole action is mostly involving fluorine. So I think I've explained it over and over again. So in this, we'll see it. I don't want to give you the exercise to do it. I know most of you will not even attempt, because you don't even know the element xenon is a halogen. No, it's not a halogen, it's a noble gas. One of those noble gases down that still are kind of reactable gases. So you just draw it roughly, a sketch, and then you work out the 4 times 7, which is the 7 around the fluorine, multiplied by 4, which is the 4 of them, plus 8. Notice that the 8 is for xenon. Xenon has complete electrons, but it's one of those strange situations where you have a noble gas still reacting, because the electrons are far away from the nucleus. Hence, an atom that is very electronegative can decide to pull its electrons from it, and hence you can have this kind of situation. So that's the explanation for it, in case some of you are having headache trying to wonder how, and there's a noble gas reacting. So you have situations like that, and in that situations you'll have an expanded octet, where if you do your maths, you discover that, okay, you have 36, and this 36, when you find your available electrons, you see 28, and then you're trying to work out the needed, you see 24, and then you discover there's a big difference between the 28 and 24, which is 4 extra electrons. Hence you have to add that 4 extra on the xenon. So at the end of the day, most of the times you have to add the same pattern with chlorine, the one we just did involving chlorine and fluorine. Hence you repeat that situation and add the 4 extra, sorry. You had 2 extra in the previous for chlorine. In this case, you're adding 4 to balance things up. So actually, molecular geometry is a wonderful topic, but I discussed with the lecturer teaching the other group. This will not come out in your exams, but I'll just explain it for those who are interested to follow. So you can skip this part of the video to where it ends, but please be careful. Don't skip the part that is part of the lecture. So just patiently, I'll just be quick. So the idea is molecular geometry. So it's just shapes of molecules or structures of molecules, any which one you prefer. Geometries. So diatomic molecules are the easiest to visualize in 3 dimensions. So the reason why diatomic molecules are the easier to visualize because the molecules are in pairs and it's easy. But the other ones, which are the para or the diradicals and all of those other ones, because they are paramagnetic, they are a little bit complicated and they are not easy to understand because of the irregularities. You have things like expanded octets, all of those different things that can happen as a result of slight differences, and it's almost like you're trying to represent them, but you can't very accurately do so. You can do so with a certain degree of accuracy, but not perfect. The same way an artist that is not too good will struggle to draw a face, but can easily draw a table, a chair, because those things don't require super skills to do. You can do a quick sketch, but for things that have a lot of details, it's harder. So that's me trying to explain. So you have hydrogen chloride and chlorine gas, sorry. So the diatomic molecules are linear. So diatomic molecules just straight. They involve 2 atoms straight. So it's very easy to picture what they look like because it's just 2 of them. Just draw one line between the 2 of them and that's it. So you have 2 electron pairs, which is either a linear one, a bent one, or bond angles. So when you have 2 pairs, you just have a situation where you can either have a straight line or something that is bent, something that's like this, either straight or bent, and then you can have an angle that is 180 or an angle that is bent, which is less than 180, which can be 90, 45, depends on what kind of angle or how much pushed it is to form the angle. So always 180 in the linear and then less than 180 in the bent. As I said, linear is like this, then bent is like this. So it's 180 or less than 180. Those of us that know geometry will enjoy ourselves. So we have the VSEPR theory, and I told you previously, now we're looking at it. It's your valence shell electron pair repulsion theory. What it simply means is that there's a theory that explains the shape of a molecule or compound on the strength of the electron pairs that are present or absent. I hope that works. So ideal geometry of molecules is determined by the way the electron pairs orient themselves in space. Orientation of electron pairs arises from electron repulsion. Electron pairs spread out so as to minimize repulsion. Remember when we started the lectures, I talked about when you have pairs of electrons. For these pairs to come together, lessen the energy. And once you have pairs around, it tends to be a lot of energy. So when you have lone pairs, interesting. So you have examples that we're going to be seeing to explain this whole concept of electrons. We started from talking about electron structure and the periodic table, all of those things with regards to electron, talking about how they are in space and all of those things, just to build our minds for this. So very good examples. Now you see the balloons. balloons. We talked about gases. The balloons are not just arranged, if you get two balloons, tie them head on, you have the linear. If you get three, tie them heads on, you get this trigonal planar. So it's like a triangle in a plane. And then when you get four balloons and tie them, notice that you're gonna have the trigonal planar and then the one at the top, which makes it tetrahedral. Tetra means four sides. Hedral is just shape. Has to do with the hedral shape. It's like a heel. Tetrahedral. Then the part where you now have multiple, where you now have trigonal bipyramid, where you have a pyramid up and pyramid down. That's the bi. That's bi is two pyramids on themselves. So, and then you have the octahedral. Now you know that you're talking about 8. We have like 1, 2, 3, 4, 5, 6, 7, 8. You have like the whole shape around themselves, to form that 8 ends. Tetrahedral is 4 sides. Then octahedral is a bihedral. Is a bitetrahedral. I hope that makes sense to somebody. You have your tetrahedral, and then you have another tetrahedral underneath it. That's your octahedral. Then for your trigonal, you have one trigonal and another trigonal. That's your trigonal pyramidal. But notice it has an addition of the linear on it, where you have your okay, let's put it like this. It's your trigonal planar with a linear on the top is what gives you your bi. It's just there's the plane and then there's the linear in between it that makes it pyramid, up and down. So that's it. So you have your 2, 3, 4, 5, and 6. 2, 3, 4, 5, and 6. So this is trying to explain what the geometries of atoms bonded will look like, minus the possibility of notice that including the possibility of lone pairs as well, which will push down things around. So let's go into it. So you have just explaining it in detail, linear, straightforward. Just when two things bond, this is what you get, linear, no brainer. It's either it's linear or it's bent on the strength of the lone pairs around about it. So it's trigonal planar. Notice that in this case you have 3 in trigonal planar and then 4 in tetrahedral. So you have 3, and notice their names have their trigonal 3 sides, tetrahedral 4. How many heels? So knowing their Greek Latin naming helps you quickly pick on it. So the electron pairs formed are equilateral triangle around the central atom. The word equilateral triangle. So it's an equilateral triangle. So you have 1 triangle, 2 triangle, and then another 3 triangle, which is just 3 balloons docking themselves. So the angle is 120. Then for tetrahedral, you have that whole thing we talked about, that 1 here and then 3 around it, which is your 109.5 degrees. So you have your trigonal bipyramid. Your trigonal bipyramid is now your bond angles vary at different sides. So in the trigonal plane you have 120. Then in the apex area, that's the peak of it, you have 90. And then in the central part, which is I'll show us with this. Can I do that here? Yeah, okay. So this place the bond angles here is different from the bond angles here, is different from the bond angles at the top itself. Again, when you top like this, different angle, this different angle, then the 1, 2, then the central part of it. So you have different sides, so hence you have different, so the 180 apex area, then the one straight down, you have the straight down, the one that's like this, and then the one between the trigonal end, which is similar to the trigonal plane as we saw. So the octahedron, which is just a square bipyramidal. Notice that they are using their names interchangeably. There is your square, 4 corners bipyramid, and then you have a tri-bipyramid, which is just a build-up on itself. So you have the 190, 180 on the opposite sides. That's the 2 angles. So this is just going to detail. The A is your central, the X is your attachment, and then we'll see E ahead. So we have examples. It's 180, 120, 109.5. So we have, this one has 5 and 6 attachments. The 6 attachments is your tetrahedron, remember. The 5 is your trigonal bipyramid. Then you have the angles that we talked about. Then you have an example, and then you have different shapes. So notice that unshared pairs of electrons affect the geometry. Unshared pairs of electrons affect the geometry. I'll explain that. So same as what single bonds are involved, the effect. It's the same as when single bonds are involved. You have bond angles are smaller than the ideal values, so they are small on the strength of that electron pair geometry. And then the molecular geometry we have been talking about, that's what we're talking about. It's quite different from one or more shear pairs of pairs present. So while describing only the disposition of the bonded electron I referred, so when you're talking about the position of the bonded, or unbonded too has its influence, and we see that with ammonia. Normally ammonia is bonded in 3 places, but what we fail to realize most times is that there's a lone pair, and because of the presence of this lone pair, it shifts the bonds downwards. Hence you have a bent situation that results in a interesting geometry. Normally if you have 3 hydrogen bonding to nitrogen, you should think about trigonal planar, which is triangle on a plane, just a single plane of 3 things bonding to one thing. But because of the lone pair or the unbonded electrons, 2 pairs of electrons, a pair of electrons, not 2 pairs, pair of electrons, you have a pyramid being formed, hence the trigonal pyramidal shape of ammonia, which now explains what can happen when you have pairs of electrons hanging. So there's a E now for unshared pair of electrons to make our ability to describe shapes or geometry of compounds compounds in detail effective. So you have the A, X and E, which is like axe. I don't know how you call it though, but some people, it's not axe. So the AXE. So you have the A which is the central, the X which is the attachment, and then the E which is your lone or unshared pairs of electrons. And for that you have certain situations or certain shapes. So notice that for AXE you have your trigonal, AX, two X's and then one E is bent. which is different from AX3, because your AX3 is your normal stuff. Then with the presence of an E, it makes it bent instead of your trigonal planar. This is what I was explaining with ammonia. So ammonia now becomes evident in AX3E, which is what we're talking about. You have normally AX3 should be trigonal planar, but because you have an E, which is a unshared electron, it bends it, and then that bend will result in a trigonal pyramid. Notice there's trigonal pyramid and there's trigonal bipyramid, so don't confuse yourself. Not that the names explain who they are. You can't confuse names if you're sure of who it is, but if you're not sure, then you can confuse the names. So bond angles and lone pairs, ammonia is the one we talked about a lot, and then water is bent as well. I think we saw an example. The example used was in water, but water too is bent. Okay, sorry, water is here. It's bent as well. So this one has two attachments, which two atoms attach a terminal, call them number of terminal atoms, and then we have the unshared. So water has one central, which is your oxygen, and two attachment, and then oxygen has two lone unshared pairs, so hence it falls under bent. So that's nice that we know that number of unshared pairs of electron also influences it even greatly, because AX2E is bent, AX2E2 is also bent, and it's not in any way trigonal pyramidal or pyramid, a trigonal pyramid. So you have ammonia water show smaller bond angles than predicted from the ideal geometry. So ideal geometry will be linear if you look at water, but because of the situation of the unshared pairs of electron, we now see that this helps us to see that it's bent, and it's something you can draw it, because that's why understanding Lewis structure helps us understand the shape, the bond angles, and that's why Lewis structure is very helpful, because it tells you that you can just draw it and forget that there are electrons or unshared electrons around about it which can influence its shape. So that's why it's very important. So lone pair is larger in volume than the bond pair, just to explain the fact that once you have a lone pair, it has power and it can push it. Just think about it. If you're thinking about a house, the person that stays in or owns a house has the power to kick you out and bring you in. He might not be the one that built the house, but because he, for that point in time, stays there and owns the place, he can tell you, oh, you have overstayed, you're welcome, leave. So hence the whole idea of the lone pairs of electron getting to push the other persons that are sharing the electron. I fact it makes sense. If you're squatting with somebody, you can't be telling them what to do or to move to the other place, or except if that's very strange. There are people that can do that. So nucleus exists in only one end of the bond, so the electrons are free to spread out and over a large area in space. So this is to predict the geometry of ammonium ion and this boron trifluoride, and then this phosphorus trichloride. So I just called the names so that, but normally you should be the one telling me the names, but I called it because I'm here and you're not here. Okay, so but I think next time I'll ask you to guess the names of tell the names before I speak. So let's just, well, you can attempt to do this, given that you know what, if you understood what we did. So just try and do it first. Pause it and try and do it and see. You're in your room, nobody's going to know that you failed it, so just pause. Okay, then the strategy is the A, which is the central, the X, which is the terminal, number of terminals, and then the E, which is the unshared bond, unshared electrons. So we ask ourselves first and foremost, what is the central? Looking at it, you know that N is the central for ammonium, B is the central for the boron trifluoride, and then P is the central for the other. Then what are the attachments? You have 4 attachments, 3 attachments, and 3 attachments. Then what are the lone pairs? That's just how you're going to do it. So in the first situation, we have this. So NX is 4. Then you say, is there any lone, any unshared electrons? No. So it's tetrahedral straight up, because you know that's 4 to the central. So in this case, now you have B, which is central, X, which is 3. Is there any E? No. If there's no E, it's just straightforward. It's a trigonal planar. The angle is 120. Notice that the previous is 109.5. And the last one, you have your P, Cl3, no E, so is there E? Okay, there's one E. Yeah, there's one E. So because of that one E now, one E, it pushes the other ones down. Hence, you now have a diagonal pyramid, and it's 109.5, and then you have 104. So this is the whole thing we are very much aware: the central, terminal, and then the lone pair. So oxygen has central, water has central, which is oxygen, has 2 attachments of hydrogen, and then has 2 lone pairs of electrons. So hence it pushes it, forces those 2 down, and then you have a bent shape. So very important. So we have and then remember we talked about expanded octet, which makes it a lot interesting for this one. So the shape now becomes complicated. So please try as much as possible to not have your brains swarm in the complication. Just understand it and then be going on with it. So for xenon tetrafluoride, remember we saw the shape before. So now you have it as a central, 4 attachments, and then 2 lone pairs. So hence you're going to have it in such a way that it's almost like a spindle, where they are trying to avoid the influence of the lone pairs. So they'll just find themselves in the center and to be going like a steering, like a spindle. I think that's what they call it, a spindle. A spindle. Then you have the shape like that. And notice that this is how new structures are designed, or shapes, or micro machines. If you are interested in nanotechnology, this is how they are designed. Like, I think I taught nanotechnology some years back. So it's very fascinating, and that's how the whole idea of chemistry works. With this understanding, you can create compounds or designs and all of those things that happens around about in chemistry. So we have the multiple bonds, and in this case now we're talking about the double bonds and all of those things and how it works with them. So I think we might finish this lecture. Let me see. Okay, let me do this. Okay. I think what is going to happen is we'll end it for this part and continue in the next lecture. So we ended this lecture here, and this is the end of part 2. So be on the lookout for part 3, which is going to be shortly.